Hello, and welcome to this exciting demonstration of the Goldbach Conjecture test in Python. My name is Professor Charles, and I'm thrilled to show you how we can use programming to explore one of the most intriguing unsolved problems in mathematics. The Goldbach Conjecture has puzzled mathematicians for centuries, and we'll see how Python can help us test it for a range of even numbers. As a mathematician and computer scientist, I've spent years studying the Goldbach Conjecture, and I'm excited to share my knowledge with you. In this video, I'll demonstrate how to write a program that tests a conjecture, and we'll see how it performs in practice. I'll walk you through the code, explaining each step and providing insights into the theory behind it. By the end of this video, you'll have a better understanding of the Goldbach conjecture and how Python can be used to explore complex mathematical problems. So sit back, relax, and get ready for an informative and engaging demonstration of the Goldbach conjecture test in Python presented by me, Professor Charles. Goldbach's conjecture is a well-known unsolved problem in number theory. It was first proposed by Christian Goldbach in 1742, and since then it has remained unsolved. The conjecture states that every even number greater than 2 can be expressed as the sum of two prime numbers. The problem has fascinated mathematicians for centuries, and it continues to be a topic of research. This slide presents some examples of even numbers that satisfy Goldbach's conjecture. For instance, the number 4 can be expressed as the sum of two prime numbers which are both equal to 2. Similarly, the number 6 can be expressed as the sum of two prime numbers which can be expressed as either 3 and 3 or 5 and 1. These examples illustrate that even numbers can indeed be expressed as the sum of two prime numbers as stated by Goldbach's conjecture. This slide discusses the current status of Goldbach's conjecture. Despite being studied for over 2 centuries, the conjecture remains unsolved. However, extensive computational efforts have verified the conjecture for even numbers up to 4 times 10 to the 18. The fact that the conjecture has not been disproven for such large numbers provides some evidence that it may be true. Nevertheless, a proof of the conjecture remains elusive. This slide presents some possible approaches that mathematicians have used to try to prove Goldbach's conjecture. One approach is to analyze patterns in prime numbers to understand how they can be combined and form even numbers. Another approach is to study the distribution of prime numbers, which can provide insights into the likelihood of finding prime number pairs that add up to even numbers. Additionally, exploring the properties of even numbers can also provide clues about the conjecture. This slide emphasizes the significance of Goldbach's conjecture in mathematics. The conjecture has captured the attention of mathematicians and the public for centuries, and it has led to the development of new theories and techniques in number theory. Proving or disproving the conjecture would be a significant accomplishment, as it would shed light on one of the oldest and most intriguing problems in mathematics. Moreover, it would have implications for other areas of mathematics and science that rely on number theory. As a math enthusiast and programmer, I was intrigued by Goldbach's conjecture and wanted to explore it further, so I decided to create a program to test that conjecture for various even integers. My program takes an even integer as input and checks whether it can be expressed as the sum of two prime numbers. If it can, the program outputs the two prime numbers that add up to it. If it cannot, the program indicates that Goldbach conjecture does not hold true for that particular integer. While my program cannot prove or disprove Goldbach's conjecture definitively, it can help to shed light on the conjecture and provide further evidence for or against its validity. I'm excited to see what my program will reveal about this fascinating problem, and I hope you'll join me on this journey of discovery. Thank you for watching. So first things first, we're going to create a isPrime function. We're going to create a Goldbach conjecture function, and then we're going to also create a for loop, and then a pair. If pairs are none, then we're going to see if the program checks to see if the pairs are none. So first things first, we're going to define a function to test whether a number is prime. This is the code I made already. F is prime n. Comments out. And this is going to return true if n is prime and false otherwise. Now we're going to check if integers between 2 and the square root of n divides n evenly. So we're going to do n is less than 2. We're going to return false. No. Return. Now we're going to create the for loop. And if no factors are found, n is going to be prime. And we're going to return false. Now we're going to define a function to test Goldbach's conjecture for a given number. I just want to explain this a little bit. So this the def is prime function right here. This function takes n as an integer, as an integer n as an input, and returns true if n is a prime number. And it's going to return false otherwise. It does this by iterating over all integers from 2 to the square root of n, which is inclusive, and checks if any of them divide n evenly. If no factors are found, then n is prime and the function returns true. Now we're going to create a function, a Goldbach conjecture, which this function is going to take an even integer n as the input and test Goldbach's conjecture for that number. Goldbach's conjecture states that every even integer greater than 2 can be expressed as the sum of two numbers. The function first checks that n is a valid even number greater than or equal to 4 and divisible by 2. It then creates a list of prime numbers less than n using the isPrime function that we defined earlier. Finally, it will generate a list of all pairs of primes that sum to n and returns this list. All right. This is how we define the Goldbach conjecture function. We're going to do if n is less than 4 or n where the remainder of n, the n divided by remainder is not equal to 0. We're going to return none. Basically what this is doing is test Goldbach's conjecture for the given even number n. It will return a list of tuples a and b that represent the two prime numbers that sum to n if such a pair exists. Now we're going to create a list of prime numbers less than n using the prime function. Prime is equal to I for I in range 2 to n if is underscore prime Now we're going to generate a list of all pairs of primes that sum to n. Then we're going to return pairs. Okay, next we're going to basically create a for loop. We're going to do I in a range of what we're going to basically test the Goldbach conjecture for even numbers between whatever range of numbers we want. This line is going to create a loop that can iterate over all even integers. So essentially we're going to go from A to B, and then we're going to figure out what even numbers it'll iterate over. So for I in range, we'll just keep it simple for now. And basically we're going to call the Goldbach conjecture function for each even number in the loop. We're going to check if pairs are none, indicating that Goldbach's conjecture is not true for I. And then we're going to create a message indicating that Goldbach's conjecture is not true for I. Want to save it? Essentially, when it's finishing with code 0, what we're doing is we're running a loop that tests the Goldbach conjecture for all even numbers from 4 to 1,000, which is inclusive by calling the Goldbach conjecture function for each of the even numbers. As you can see here, from 4 to 1,000, obviously this has already been proven to not be true. It's actually been proven to be true from 4 to 10 to the 18. That would be computationally expensive and highly time consuming. However, if we wanted to potentially test that, what we would do in this situation, we got 4 times 10 to the 18 here. And if someone was to try to disprove it up to, let's say, 5 to 10 to the 18, it would, on this machine that I'm running right now, it would take roughly, I think, 4 days continuously to run it. If you know, someone is using this for a project and wants to see if maybe this is true, and they have those days to spare, then this code right here will definitely perform the test. So I just interrupted, but I just want to explain right here, the def is prime function. This takes an integer n as an input and returns true if n is a prime number and false otherwise. And it's going to do this by iterating over all the integers from 2 to the square root of n inclusive, and checking if any of them divide n evenly. If no such factors are found, then n is prime and the function returns true. This function, the Goldbach conjecture, it'll take an even integer n as an input and test Goldbach conjecture for that number. Goldbach conjecture states that every even integer greater than 2 can be expressed as the sum of two prime numbers. This function first checks that n is a valid even number greater than or equal to 4 and divisible by 2. It then creates a list of prime numbers less than 4 using the isPrime function defined earlier. Finally, it'll generate a list of all pairs of primes that sum to n and return the list. Okay, this for loop, in this case, we're doing for I in range 4 times 10 to the 18 to 5 times 10 to 18. That's 4 quadrillion to 5 quadrillion, and this will create a loop that iterates over all integers evenly. And it'll do that in increments of 2. The pairs, what it's doing is for each integer I in the loop, the program calls the Goldbach integer function. So it's for each of these pairs, for each of the pairs, it's calling this function. And it'll test the Goldbach conjecture for that number. The pairs of prime from the sum to I are returned and stored in the pairs variable. If the pairs are this line of code right here, if pairs is none, it'll print Goldbach's conjecture is not true for whatever integer. And like I said, this code is implementation of a test of Goldbach conjecture, in this case for a range of even numbers from 4 quadrillion to 5 quadrillion. The program defines two functions to test whether a given number is prime and to test Goldbach's conjecture for a given even number, and then uses a loop to test the conjecture for each even number in the specified range. If no pairs of primes are found that sum to an even number, the program report that Goldbach's conjecture is not true for that number. I just want to say thank you for watching my video. Hope you guys tune in for more content.